hey everyone, my name is Fazl, and I'm going to be describing some of my work, and yeah, most of it will be the type of things that I've been working on, so purposefully I'll be rushing through them because of time constraints, but there are two main things that I want to leave you with, and if you're interested in the things that I rush through, please come and talk to me afterwards. So a lot of these works are joint work with other people, so credit to them. Great, so the first thing that I want to leave you with, and the thing that I've spent a lot of my time, is how do you go about conducting mechanistic interpretability? We have heard a lot of people talk about different approaches for interpretability, but the one thing that has worked for us, and this is the recipe of my friend Adria, and it goes as follows. You choose a behavior that you want to understand and you want to interpret. You want to basically observe that behavior. So for example, you figure out that there's a particular neuron that corresponds to or detects a particular concept like hate, love, whatsoever. And then you want to create a data set that allows you to reproduce that behavior. So it could be Shakespeare's poems, it could be some newspaper or some tweets by Trump, etc. Then you want to find also a measure that allows you to go about measuring that behavior is in fact happening. Then you want to think about different levels of granularity. So do you want to think about, okay, I want to think about in terms of attention heads, I want to think about query key value pairs, or I want to think about token positions. There is no, unfortunately, like one particular or one ground truth way of doing this, so it's pretty much experimental. And different people go about this work differently. And then you could do some sort of activation patching, etc., to find what sort of behaviors are involved in this network. And then you go back to 1B and you choose a slightly different data set, labels or circuits, and you basically iterate through this process until you're happy with what you've been doing. So now that I've given you an idea of how mechanistic interpretability works at least in the community that I'm involved in, I'm going to walk through very quickly some of my previous work, and then I'll leave you with some of the things that I'm excited about doing going forward. So when I started thinking about interpretability, I thought, oh, maybe the reason why we don't understand these models is because they're small enough. They're too small. If we increase the size, maybe we'll be able to understand them. So in this work, that was actually supposed to be in Toronto, presenting it today, somebody else had to go, so it's okay. We show that, in fact, when you increase the parameter size of these models, their performance in terms of like truthfulness, etc., decreases. So in here, we show that large language models prefer incorrect but statistically likely misconception completion of Python code versus smaller models. So smaller models would tell you that, I don't know, no comment, but larger models would be able to convince you that this is in fact a correct completion. So we wanted to know, like, hey, what is happening? So there's this phenomenon of if you understand what is happening inside a model, and if it's not behaving in the way that you expect it to behave, you can edit these models. So David Bau's group have done a lot about editing. So we wanted to know, does edit really work? Where does edits go wrong? So in this work, we basically show that methods like Rome and Mehmet, the two famous model editing papers, have a lot of shortcomings. That when you edit one particular association or fact, it also affects other facts about that fact. So for example, in here, we edit, hypothetically imagine that the Louvre is in Rome. So like we want the model to believe that the Louvre is in Rome. And then we want to test the model's knowledge in other factual associations. So the Louvre is cool. Obama was born. It still thinks Obama was born in Rome. And the numbers in the brackets is the logits. And then we ask, the Louvre is an art museum. His Holiness the Dalai Lama resides in. Then it figures out that there's some religious association between Tibetan and Vatican. So it thinks that Dalai resides in Vatican. Then we were like, okay, so can we like zoom in? Can we try to understand what is going on? Why does it make this type of mistakes? And in this work, we basically come up with a new method that allows you to investigate individual neurons at scale. So yeah, happy to talk more about this. But the basic premise is you get a data set, you find the most activating neurons in that data set, then you try to prune everything after the most activating neuron, because these are autoregressive models, tokens that happen to be after the most activating token should not affect the most activating token, then you observe the behavior, so forth and so on. And then we can visualize a graphical representation of the data set that allows us to eyeball what is happening in this particular model. Then we were like, okay, well, it seems like none of this is working, so let's now go and investigate the relationship between attention heads and neuron interaction. So typically, a lot of work by, the circuits work by Chris, etc. They're either studying attention heads individually or the MLP layers, but they never look at their interaction. So in this work, we basically borrow some of the tools that we built in Neuron to Graph. We find the most activating tokens. Then we try to get a model like GPT-4 to explain the phenomena. Like, can GPT-4, if we give it the most activating neurons, explain whether or not this attention head is active? And this allows us to have some further understanding of what is happening inside these models. So then we also see that basically no matter what happens, these models are neuroplastic. What I mean by neuroplastic is that even if you edit the knowledge completely from these models, as in set the weight of a particular neuron to 0, and you retrain the model on a different data set, they're able to relearn the same concept exactly after 4 epochs across different data sets. So maybe we have to do more work if we want to remove concepts that are undesirable, hate, or if there's a concept of gender in a task that gender should not be present at all. So, great. So what does all of this mean? How useful is this? Can this give us anything in terms of where we want to be with safety and alignment? And the work that I'm very excited about, and the work that I've been doing in the past 3 months, is rather than trying to understand and analyze the inner mechanisms of models, is can we train humans to recognize patterns in these models and predict their behavior as to stop bad outcomes from happening if we can observe bad behaviors priorly. So we model this as a point-wise mutual information between what the model is telling us and what the human's understanding of the model might be. So I'll skip through the formalism, and I'll show you some graphical representation. So what we do is we train a meta-learner, and the idea here is that in the meta-learning domain, models are exposed to data from outside of the distribution they were trained on at test time. So their attention pattern or whatever they are most attending to might be somewhat similar to how humans think about when they see a new problem, the problem that they have never seen before. And then we bring in groups of humans, and we try to see how does random attention, different approaches to computing attention affect humans' ability to predict what the model is going to do and what the ground truth might be. And we then essentially record the time it takes plus how accurate they are in these 2 different propositions. And the idea here is that ideally, a model that is more interpretable to the human, it should take them less time to come up with an answer. So this looks something like this. So we provide them with questions, and the different shades of the text corresponds to like the weight of the attention, basically. We want to see whether or not there is any effect in humans learning to observe attention patterns of models, and whether or not this will allow them to predict bad behaviors from happening. So yeah, this is what I'm excited about. I don't know where this might go, but if you have any questions or any thoughts, I'd be very glad to discuss this with you. Thank you.
Thank you. Does anyone have a question? Do you have a challenge?
So the challenge, I guess, for a lot of people in this community is, great, we understand a couple of neurons, a couple of attention heads, there are trillions of them. How do we scale them? And if we do figure out a way to scale them, does this actually give us anything? A lot of people, including the team in Conjecture, believes that interpretability is actually harmful. So I don't really know whether it's true or false, but I'm happy to learn from the rest of you in here. So
how do we scale?
So can we scale interpretability to full model sizes? And if we learn to scale them, are there ways that this is actually going to give us the guarantees we need for safety and alignment?
Okay.
Thank you.
Great. Thank you so much, Fazl.
Thank you.